All right. So we've talked about the mole ratio step before. We've talked about the mole ratio. But what the mole ratio is, it's a conversion factor within our T-chart that allows us to convert between two different substances. So far in our T-charts, we've gone from moles of one substance to grams of the same substance. Now we're going to look at, if we put in grams of a reactant, how many grams of our product can we get out? Those are two different substances. So the mole ratio step is the conversion factor we use to do that. Okay, so mole ratio is a conversion factor. And it's really, really, really easy to see mole ratios once you kind of get what we're talking about here. You don't have to write down this balanced formula, balanced equation. Okay, I'm just going to show you what the mole ratio is in this, and you'll start to see it in other chemical reactions. Okay? Before we get into the actual question about the mole ratio, I want you to review a couple things here. Is our equation balanced? Check your atoms on each side. Give me a yes or a no if we think the equation is balanced. Okay, let's see. Potassiums on the left, how many do we have? 2. And on the right we have 2. Cl on the left we have 2, and on the right we have 2. Oxygen on the left we have 3 times 2, which is 6, and we have 2 times 3, which is 6. So yes, that's a balanced reaction, right? Second question, it says, what type of reaction is this? We talked about 4 main types, maybe 5 main types of chemical reactions. Anyone remember what this kind might be? Right, and we did the lab with it. We have one molecule being broken down into 2 simpler molecules. What's another word for breaking down? Yeah, decomposition, right? Decomposition is when we take a complex molecule and we break it down into simpler molecules, right? When something decomposes, it breaks down. So it's the same thing that's happening here. We've got one big molecule that's breaking down into smaller. Okay, so that's a decomposition reaction. Okay, what's the mole ratio between potassium chlorate and oxygen? Okay, oxygen gas and potassium chlorate. When we look for the mole ratio, all we're looking for is the coefficient that sits in front. That's it, right? This reaction, if I read it out loud, it says 2 moles of potassium chlorate yields 2 moles of potassium chloride and 3 moles of oxygen, right? That's what I'm saying. As I say it out loud, we say 2 moles of potassium chlorate breaks down and yields 2 moles of potassium chloride and 3 moles of oxygen. Okay? So as I look for the mole ratio between potassium chlorate and oxygen, I say it's 2, 2, 3. Right? 2 moles of this molecule yield 3 moles of this molecule. So when we look at the mole ratio, all we're looking at is the coefficient that sits in front of that compound. Okay? That will be used in our T-chart as a conversion factor. We did this just for a little bit in percent composition, but it'll be a little bit more clear, I think, today. Okay? So in this reaction, it takes 2 moles of potassium chlorate in order to make 3 moles of oxygen. Okay? That's what our mole ratio tells us. I want you to go ahead and balance this equation. Let's get some practice balancing, and then we're going to talk about mole ratio within that equation. The lines in front of it are just like little spots for you to put your coefficient, so don't let that mess you up. Okay, Jensen, can you give me your coefficients?
I got 2 internal AG and 1
This one?
Yeah.
Okay, so this one was a 1?
Yeah.
Okay.
And then I got 1 and
We agree? 1, 2, 1, 2. Okay, perfect. So we balanced our equation. Now it wants to know what's the mole ratio between copper and silver. What's the mole ratio?
2.
1 to 2. 1 to 2. Okay? We're not going to write it like that very often, but you need to be able to apply this concept of the mole ratio when we start doing conversions. Okay? We don't write it in this ratio form very often, right? We're not going to say the ratio is 1 to 2. That's not how we express this knowledge, right? The knowledge of the mole ratio will apply when we put it into our T-chart. Okay? So we're going to start now in the simplest type of conversion with stoichiometry, and that's going from moles of a reactant to moles of a product. And it's a really simple conversion. Okay? This is going to take our amount of a given substance, usually in moles, or for now in moles, and then convert it to moles of our unknown substance. Okay, so I'm going to go ahead and balance the formula for you, and then we're going to start looking at how we answer this question. How many moles of lithium hydroxide are required to react with 20 moles of carbon dioxide? Okay, do we agree that it's balanced here? Okay, I think I hit everything. 1 carbon on each side, 4 oxygens. On the left, 1, 2, 3, 4, 1, 2, 3, 4, and then 2 hydrogens, 1, 2, and 1, 2. Okay, so now I want to go about answering that question. Answering that question of how we find out moles of our lithium hydroxide and moles of carbon dioxide, given that we're starting with 20 moles. Okay, and this is just a proportion problem. We're going to put it into our T-chart so we can see that proportion. Okay, so if I start with 20 moles of carbon dioxide, I want to find out how many moles of lithium hydroxide will it take to complete the reaction, right? How many moles of lithium hydroxide will it take to make that reaction go all the way to completion? So I want to use up all 20 moles of that carbon dioxide. So I start with my T-chart in what I know, right? I always start my T-chart with what I know, every time. Okay, and I want to go from moles of carbon dioxide, and I want to end up in moles of lithium hydroxide. Okay, so when you start doing these stoichiometry problems, I like to kind of write above my balanced formula what I'm looking at. So sometimes I'll go 20 moles, and then here I write my question mark. Right? So I know these are the 2 chemical formulas, or these are the 2 compounds that I need to be paying attention to, basically. Okay? So I want to go from moles of carbon dioxide to moles of lithium hydroxide. Okay? So I start my T-chart with what I know. I want to cancel moles of carbon dioxide, so automatically where does that go? Bottom. Moles of CO2. And what's my goal? What do I need to end up in? Moles of lithium hydroxide. So it can go here. Moles of lithium hydroxide. So this step, maybe do it in a different color. This step right here is called that mole ratio step. See how I have moles on top and on bottom? And I have 2 different formulas. The only time, the absolute only time you can have 2 different formulas in the same column of your T-chart is in this mole ratio step. That's the only time. You can't go from grams of carbon dioxide to moles of lithium in the same step. Okay? The only place you can have 2 different chemical compounds in the same part of your T-chart is in that mole ratio step. Okay? And so up until this point, I drilled into your minds that moles gets the 1, right? Mole ratio step, that goes out the window. Okay? In this step, you take these numbers directly from the periodic table. Okay? When we talked about our mole ratio, this is where it's coming into play. So moles of carbon dioxide is a 1 because it comes right from the periodic table. So what number would go with moles of lithium hydroxide? 2. Okay? These numbers within our mole ratio step come right from our balance formula. Okay? So I've canceled moles of carbon dioxide. I'm left with moles of lithium hydroxide, which is exactly what I want. And if I multiply across, I get 40 moles of lithium hydroxide. Okay? Does that make sense? If you look at your formula and you say 1 mole of carbon dioxide and 2 moles of lithium hydroxide yields this, it should make sense that if we started with 20 moles, we need double that amount of lithium hydroxide, right? It takes 2 moles of lithium hydroxide combined with 1 mole to get our product. So if I start with 20 moles, it should make sense then that I need double of that other product because of its mole ratio. Mm-hmm.
So is it just like a substitution from the numbers in the problem to the numbers in the balance sheet?
Is that what we had for balancing? Okay. If you're not getting that or you have questions about how I got that balance formula, now would be the time. Okay, how many moles of O2 will result from the decomposition of 5 moles of hydrogen peroxide? So my goal is to go to moles, right? I want to find out how many moles of O2 is from 5 moles of hydrogen peroxide, right? And you don't have to write it above the formula. It just helps me look at, these are the 2 mole ratios I need so I don't accidentally misread that. All right, so I start with what I know, 5 moles of H2O2. If you don't know what hydrogen peroxide is, how can you come up with the fact that it's this? You know this one's not hydrogen peroxide, you know this one's not hydrogen peroxide, so that means it's got to be this one. Right? We haven't learned a name like that, so it's not a big deal, but you should be able to, process of elimination, figure out that one's hydrogen peroxide. All right, so we start with what we know, 5 moles of H2O2, and we want to end up in moles of oxygen. All right, so we take our moles of H2O2, we cancel them here, and then what can go on the top? Moles of O2, right? Because I can go from moles of one substance to moles of another. Okay? That's my mole ratio step. So what number goes here with hydrogen peroxide? 2. And what number goes with oxygen gas? 1. Those numbers are coming right from our periodic table. I'm not periodic table, sorry. Right from our balanced chemical reaction. Okay? So the 1 is coming here. The 2 is coming here. Okay, so we multiply across the whole top, divide by the whole bottom, and we get 2.5 moles of O2. Okay, it's really easy to see when you have these nice, like, easy numbers. Right? It's when we get a little bit more realistic numbers that it can be a little bit more difficult to see. Okay?
Doesn't matter if it's a fraction.
I don't like fractions. I just like decimal places.
No, I mean, I thought you couldn't have like a decimal number in front of something in like a balance sheet.
We won't put it into a balance formula. This is saying if we start with 5 moles of hydrogen peroxide, how many moles of oxygen will we get out? So that wouldn't go into our balance formula because this is always the most reduced version. Okay? So this is just saying if we literally put in 5 moles into a reaction, how much oxygen gas would we get out? It would be 2.5 moles. Okay? Questions with these conversions? Mole to mole. Okay. Now we're going to take it a step further and we're going to go moles to grams or grams to moles. Okay? We're going to start with one or the other if we're going to start in moles, and then we're going to go to grams, or we're going to start in grams and go to moles. Okay? So it's basically adding one more section to our T-chart. So here's our formula down here. I'll go ahead and balance it for you, since that's not really what we need to be focused on at this point. Oh, that doesn't work. Nope. Okay, does that balance equation look okay? I had to fix here because I left, when I was doing oxygens, I left out these 6. Okay, so oxygens on the right, I had 12 plus 6, which is 18. I have 6 here, so that means I need 12, which is where I got the 6. Right, O2. Okay, so we're feeling good about balance equation. Okay, how many, I guess it's asking it a little differently. What mass in grams of glucose is produced when 3 moles of water reacts with carbon dioxide? Okay, so that means we start with 3 moles of water, and we want to know how many grams. Okay, what mass, whenever it asks for mass, that means we're going to grams, right? We're using grams. What mass of grams of glucose is produced when 3 moles of water reacts with carbon dioxide? So this is a little bit less clear to just look at and be able to see the ratio. We want to go all the way to grams here, which means we need our T-chart. So we're going to start with what we know. 3 moles of water. And my goal is to end up in grams of of glucose. Can I go directly from moles of water to grams of glucose? No. What do I have to be in if I want to go from one substance to another? Moles. I have to go mole to mole. So next comes my mole ratio step. I say moles of water to moles of glucose, C6H12O6. So how did I know that moles of water had to go here? Yeah, I just need to cancel, right? If you're stuck about where to start, right, cancel your units and then decide where you can go from there. So what numbers go in my T-chart? What number goes here? A 6, and that comes from this, right here in our balanced chemical equation, right? 6 moles of water are required. So I take 6 moles. What's the mole ratio between water and glucose, right? What number goes here? A 1. Okay? So what this is saying, I want you to just think this through. In order to produce 1 mole of glucose, in order to produce 1 mole, right, because a mole, 1 goes there. In order to produce 1 mole, I have to put in 6 moles of carbon dioxide and 6 moles of water. Otherwise, I won't produce a mole of glucose. Okay, that's what we need to be thinking about here. Okay, so I've canceled my 6 moles of water. Now I need to cancel moles of glucose and go to what? I need to go to grams of glucose. So now we're back to our old rule of mole gets the 1. And then what number goes here with grams? Molar mass. Always. With grams is molar mass. So we need to calculate the molar mass of glucose to go there. Okay, the molar mass of glucose came out to be 180. I multiplied across the whole top, divided by the whole bottom, and I ended up with 90 grams of glucose. 90 grams of glucose. So I took 3 times 180, then I take that divided by 6. Okay? Now I want you to just think about the big picture here for a second. We said that in order to produce 1 mole of glucose, you had to put in 6 moles of water. But we only put in 3. We put in half of that. Agree? Yes, are we seeing that? We needed 6 to produce 1 mole. We only put in 3. So we should come out with half a mole of glucose, which is what we did. Right? 180 grams is the mass of 1 mole of glucose. We ended up with 90 grams. So we came out with exactly half. Do we see that ratio and how that works? Okay, these are like easy, nice, round numbers, right? It's when we get a little bit more realistic numbers that it changes, okay? But I want you to see the ratio, that these numbers are not arbitrary. This is exactly what's happening, okay? Any questions? Okay. I want you to try this one on your own. How many grams of water are produced if 2.2 moles of NH3 are combined with excess oxygen? That excess oxygen statement doesn't mean a whole lot to you now, and it doesn't need to. You're going from 2.2 moles of ammonia to grams of water. Is that about what you had? 59.6? Okay, see how it's a little bit different, or a little bit more difficult. We didn't start with a nice, pretty number. It was easily divisible by its original mole, right? It's not it's easy to see here. But the math works every time. Okay, if you want to think about big picture, we started with less than what we said was required, right, in order to form 6 moles. So 6 moles times 18 would have been greater than 59.6, right? You don't have to be thinking about that big process, but it's a way for you to help self-check a little bit. Okay? Any questions about what was the process of setting up your T-chart? Yeah, Allison.
So, do you not distribute the 6 on H2O to get the 2?
Okay, so we don't want to multiply by 6 2 times, right? This is why the 6 is here in that mole ratio step. So when we go here, we say 1 mole of water weighs 18. 1 mole of water doesn't weigh 18 times 1 mole of water doesn't weigh 108, right? It only weighs 18. So that's why when we go back from moles to grams, we go back to our regular rules of moles gets the 1, regular molar mass goes here. Okay? That's a really good question. We don't want to multiply by 6 2 times. That's why it goes here. Okay? So in this moles to grams step, it's just regular 1 mole and molar mass. Yeah?
Can we reduce our ratio if it's like 6?
Yeah, you can. You can. You're still going to have to... Yeah. Yes, you can. If it's like a 2 to 2, right, super useful to reduce. Here, you're still plugging something into your calculator, so it doesn't really matter. But yeah, you can. Any other questions? You ready to take another step? Build it even bigger? Okay. Let's try this one. We're working, it's the same type of step. We're not going to move forward just yet. How many grams of O2 are required to produce 0.3 moles of water? So this time we're asking how much of our reactant is necessary to get this much product. It does not change the way you solve it, just it's working in reverse. Okay, it does not change the way you solve it. You're still starting with 0.3 moles of water, and now you're working backward to get grams of oxygen gas. All right, so in this one we start with what we know, 0.3 moles of water. And we go from moles of water to moles of oxygen gas. Why is oxygen gas written O2? Do you remember what that's called? There's a word for that. There's 7 of them that have to be paired. Remember what those are called? Yeah, a diatomic. Okay, so oxygen is a diatomic. It can exist in nature by itself. It pairs with another of its kind, right? So it's O2, so that's oxygen gas. So that when we are looking at our molar mass, we say 1 mole of O2 weighs not 16 grams, but 32 grams. Okay? So we're not carrying this 5 into our molar mass, but we are carrying any subscripts. Okay, so the coefficient doesn't affect our molar mass, but any subscripts in our problem do. Okay? So it's 32 there, not 16. So when we do the multiplication, multiply across the whole top, divide by the whole bottom, we get what? 8 grams? Yeah? 0.3 times 5 times 32 divided by 6, 8 grams. Okay, questions with that? Now we're going to go one more step. Grams of a starter to grams of our final, or unknown. Grams of our known to grams of our unknown. Okay, how many grams of NO is produced if 12 grams of O2 is combined with excess ammonia? This is a lot of words that just tell us what to do, even though we know what to do. So I'm going to get rid of that. Right now, this term of excess ammonia, that's just as saying we're gonna put our 2 starter amounts. We're gonna put 12 grams of oxygen in, and we're gonna put a lot of extra ammonia. So that oxygen is the thing that's limiting our reactant, and we're gonna talk about limiting reactants later. But right now, that doesn't affect the way you solve the problem. Okay, it will later, but right now it doesn't. So I want to go from grams of oxygen, grams of O2, to grams of nitrogen monoxide. Okay? What's the thing that changes? We're not starting with moles this time. We're starting with grams. Okay? So we start with 12 grams of oxygen. So can I put my mole ratio step next? No, I need to go from grams of oxygen to moles of oxygen. Okay? So I say grams of O2 to moles of O2. Okay, see how in this section of my T-chart I still have the same chemical compound, right? I cannot switch compounds unless I am mole to mole. Okay, so same compound. What gets the 1 here? Moles gets the 1 when we're between moles and grams. And then here goes molar mass, which we know for O2 is 32. Okay, any questions about what I'm doing so far? Right, I've got to go grams of oxygen to moles of oxygen, to moles of nitrogen monoxide, to grams of nitrogen monoxide. So I'm adding one section to my T-chart, and it's this first one. Okay, so I've canceled grams of O2. Now I need to go from moles of O2 to moles of NO. And where do these numbers come from? Balanced chemical equation. Okay, so nitrogen monoxide gets a 4, and oxygen gets a 5. Okay, do we see where those numbers are coming from? Do not try to memorize the mole ratio step comes second in our T-chart. The mole ratio step comes first. That will not help you. You have got to walk through the dimensional analysis, the unit canceling parts of this T-chart. Okay? So I've canceled moles of O2. Now I go from moles of NO to grams of NO. Okay, and moles here gets the 1. Molar mass of nitrogen monoxide is 14 plus 16, which is 30 grams. Okay, so I've canceled moles of nitrogen monoxide. I've canceled moles of O2. I've canceled grams of O2. Now I multiply across the whole top, divide by the whole bottom. Do we see a pretty reasonable answer? Remember, if we're solving for grams, you should not be getting absurdly large or absurdly small numbers. Right? If we're solving for molecules, yeah, you're going to get a huge, huge, huge number. If we're solving for moles, we might get a smaller number. But we with grams, we should not be getting either a really, really large or a really, really small number. Okay. What questions do we have here? When you divide by the bottom, remember we divide by 32, divide by 5, or you do parentheses 32 times 5. Okay, really careful with that. Okay, do you see how with these stoichiometry calculations, you can now solve, you now have the tools to solve any combination of things. You could go grams to moles, or grams to grams, or grams to molecules, or molecules to molecules, or molecules to grams, or molecules to moles. You see how we can mix and match these things? You're going to have the tools to be able to solve any combination of quantities, right? If we start with this many molecules, we could say how many grams is going to come out. Or if we start with this many moles, we could say how many molecules is going to come out. We can now do any combination of these calculations, okay? Let's try a gram to gram conversion again. Let's try this one on your own. Okay, balance the equation first. How many grams of tin fluoride can be formed from 12.8 grams of hydrofluoric acid? Okay, why don't you try that one on your own? So as I multiply across the whole top, divide by the whole bottom, I get 31. 31.1 grams. Yeah? Okay, good. So balance that first, then answer those 3 separate questions. Okay, there's one of each type. I'm going to go ahead and put up those answers so that if you are done, you can check them. Okay. The process is almost exactly the same, except you don't use molar mass, you use Avogadro's number, right? So it makes it easier. We don't have to calculate molar mass. Okay? We just had this equation, so we've already balanced it before. I think this is a 4 and a 2. Right? If that many molecules of tin react with hydrofluoric acid, how many hydrogen molecules are formed? Okay? So it makes it really easy, and I'm going to show you the whole process and then show you how it kind of works out. But we're going to start with what we know. 4.21 times 10 to the 23rd of tin. I'm not going to write out molecules because it takes too much space. And we know if we're dealing with a number that big, it should be molecules. Okay? If I want to get rid of molecules, what do I need to go to? Okay, what's my process here? I'm going to go from molecules of tin to moles of tin to moles of what? Hydrogen, then to molecules of hydrogen, right? That's my 4 steps. So if I want to get rid of molecules, and I go to moles, moles gets the 1. What number goes with molecules? Right, Avogadro's number, which is 6.022 times 10 to the 23rd, right? Or we can abbreviate it NA. What step comes next? If I want to go from moles of tin to what? Moles of hydrogen, moles of H2. What's this step called? The mole ratio step. Oops. Okay, so hydrogen gets a 2, moles of tin get the 1. Now I want to get rid of moles of hydrogen and go to molecules of hydrogen. And Avogadro's number goes there as well, doesn't it? Do we see now how Avogadro's number is on the top and the bottom? Which means you can cancel that. You don't have to plug it into your calculator to multiply it and then divide by itself again. Okay, we're going to take 4.21 times 10 to the 23rd times 2. And I end up with double the amount of molecules that I started with. So 8.42 times 10 to the 23rd molecules of H2. Okay, that's it. Molecules to molecules is really easy. But now I've equipped you with the tools you need to do any type of conversion. You could go from molecules of your starting amount, and if you wanted moles of hydrogen, you would just stop right there. Right? You wouldn't bother doing the rest of that. Right? You just stop right there. You wanted to go from molecules to grams, you would go moles of hydrogen to grams of hydrogen. Okay? You now have the tools to do any type of stoichiometry conversion that you need. Right? From moles to grams, or moles to molecules, or whatever you need to do. Okay? But you have to have that mole ratio step in the middle, and you've got to just make sure that you are canceling your units correctly. Okay? All right, that is